Okay, so as always, let me just make sure that we are actually live before we start speaking. Okay, we are live on YouTube. Okay, so good afternoon, everyone. Welcome to Valongo Seminars. It's always a pleasure to have you here with us. And today, as usual, we have another very special guest to give a talk to us. So let me first give you a quick background. So my name is Luan Ghezi, and I'm a professor at Valongo Observatory, and I'm one of the organizers of the seminars, but I also have help of Douglas Brambilla, and also Ariana Cortese, and Aline Novaes also makes the art, this beautiful art that you see there on this the screen for us. So thank you all for your help, and thank you all for your presence. And today we have here with us Itziar Aretxaga. I'm sorry if I didn't say correctly, but I did my best, Itziar. And she is a senior researcher at the National Institute of Astrophysics, Optics, and Electronics in Tonantzintla, Mexico, and also a member of the Mexican Academy of Sciences. Born in Bilbao, the Basque Country, she obtained her bachelor in physics at the Complutense University of Madrid and her physics PhD at the Autonomous University of Madrid. After postdoctoral stays at the Royal Greenwich Observatory in the UK and the Max Planck Institute for Astrophysics in Germany, she joined the INAOE in 1998. Between 2006 and 2013, she coordinated the astronomy division of the Mexican Academy of Sciences, participating in the elaboration of scientific and technological development plans for the community. She's currently the scientific director of TOYTAC, polarimetric camera, and coordinates the scientific team and working groups of 10 legacy surveys that will be executed with this instrument in the upcoming 5 years. She has also been a part of the management team of the International Schools for Young Astronomers of the International Astronomical Union and is currently the director. So, Itziar, thank you very much for being here with us. Thank you for accepting our invitation. It's a great pleasure for us to have you here to give us, to let us know a little bit more about dusty galaxy in the high-redshift universe. So please feel free to go ahead and start your talk whenever you're ready.
Well, obrigada for the invitation, and good afternoon to everybody who is connected in YouTube. I'm sorry I cannot see you, and this is a very strange way of giving seminars. I'm still not used to it, but I actually do appreciate the opportunity and the, let me see, pantalla completa. To talk about the research we have been doing in Mexico. So I think I have gone into a share full screen, and now I will just project the presentation that I have to share with you. Can you confirm that you are seeing it okay?
Yes, you can go. We're seeing your screen. It's all right. Thanks.
Okay, excellent. So when I gave the talk to the title of this talk to Karin Menendez del Mestre, who basically has been the main person to get me into this adventure of talking to you remotely about the work we are doing here at INAOE. I just gave this title, and then I thought, well, high redshift. How high redshift is high redshift, right? And this depends really on your point of view. When I was a student, high redshift was anything above redshift 1. These days, if you talk to different people who actually look at the highest redshift universe, they might consider local universe redshift 1. So just bear that in mind. Just adjectives that don't have a number really can be interpreted in very different ways. But I will be speaking about galaxies, which are in the first quarter of life of the lifetime of the universe, as we see them nowadays with our telescopes. And the work that I'm going to present has been carried out not just by myself, but by a large team of people I collaborate with. And so to the left, you have the type of objects I will be talking about, like Aztec 1, one of my favorite galaxies, although today I will not basically mention this in much detail. And to the right, you have the group of people locally at the INAO I collaborate with. It's not a very recent picture. Unfortunately, we haven't been seeing each other for much of the year, as you can expect. But many of the young people here are the main workforce behind the results I will be showing you. So let me just start by putting it in context. And this is something that everybody in the astronomy department probably has gone through in their introductory cosmology lessons, and how we have a very good place framework for how the universe started and has been evolving through time. The expansion of the universe that started 13.7 billion years ago. The oldest picture we have of this universe is, of course, the cosmic microwave background that you can see here. Yes, in a deformed manner. This is, of course, the picture of the full sky that gives us the conditions in the early universe, 380,000 years after the Big Bang, and shows already fluctuations from which galaxies, larger structures like clusters of galaxies came from. Through time, the universe went on cooling and structures went on forming. And we have a sketchy picture of how galaxies went on assembling more and more mass until we just come into seeing the zoo of galaxies that are around us. So we can see here M87, the center of our own supercluster, our nearest giant galaxy, Andromeda, and some interactive galaxies like the antenna galaxies. So the name of the game for many of us is trying to figure out how from these conditions in the early universe, we came to have this very rich, inhomogeneous, and massive structure around us. Now, this is a view graph that I like to show, and this is a view graph basically that comes even from the classes that I took on galaxy formation when I was a PhD student many, many years ago. But the question posed by a simple back of the envelope calculation is still valid, and I think it goes into showing what we are trying to do with these galaxy evolution studies. So let's take, for instance, M87, this elliptical galaxy, which is very, very massive. And let's just try to figure out what type of evolution this system might have had in order to see it as we see it today. A relaxed, round system of more than 10 to the 12 solar masses of stellar mass with stellar populations. This is not exactly M87, it's another elliptical galaxy, but it goes into showing what type of stellar populations we have in elliptical galaxies. Just the presence of all these metallic lines and the presence of these very faint Balmer absorption lines, if we just analyze them in one of these diagrams and confront them with what stellar populations that we can synthesize in our computers look like, already tell us that the position of these lines, of the depth of these lines in these diagrams against the models, tell us that the stellar populations in elliptical galaxies are very old, very, very old. That's why we see them with a reddish color. But actually, we can date them. And so the black symbols already show us that elliptical galaxies the mean properties of elliptical galaxies show populations which are at least 10 gigayears old. 10 gigayears old is a very long time ago in a 13.7 billion year universe. So if we take the stellar mass we see today, let's take 3 10 to the 12 solar masses, and we say, well, if this population was formed 10 gigayears ago, we just have roughly 10, 11 gigayears ago, we roughly have around 2 gigayears to have formed all these stars. Then you come with a star formation rate that you should be seeing if you want to go back to how these elliptical galaxies formed, of around 1,000 solar masses per year. And so where are these systems? And through the history of astronomy, this type of proto-ellipticals have been looked after. I mean, in the last 30 years that I have been looking at the literature, you will see through all this time, different populations of galaxies that have been candidates for this proto-elliptical population. So I will go very quickly through this because it's not the main topic of my talk, but you will be aware that there is a population of high-redshift galaxies, which are the Lyman alpha emitters. These were proposed in the 80s and 90s, and they were searched for. And nowadays, it is routine to find these Lyman alpha emitters. These are some of the references where you can find their properties. Unfortunately, these Lyman alpha emitters, we see here one typical spectrum, a very strong Lyman alpha line with just very faint absorptions that can be nowadays be found very efficiently with emitter class telescopes, have star formation rates which are of the order of 10 solar masses per year. So they are not the 1,500 solar masses per year. This is just a rich area, a protocluster, yes, traced by these Lyman alpha emitters. But as I say, even if they can give rise to protocluster and cluster environments, very rich cluster environments, if you let them evolve through time, that's our expectation. These are not the proto-ellipticals that we are looking for. Later on, in the 19th, the Lyman break galaxies came into the game. The Lyman break galaxies, again, is a selection technique for star-forming galaxies. And basically what one does, if you take the spectrum, this is the continuum of a young population, you are looking for galaxies that do not show in the bluest filters of some photometric system, but do show in the redder filters. And this is so because this spectral energy distribution, this continuum, this will be the UV light, but redshifted into the optical observer bands. Well, when you reach the Lyman break of these galaxies, this very, very sharp drop in their continuum, then the galaxies will not be seen in the bluer filters, but they will be seen in the redder systems. So a lot of effort has gone into characterizing these Lyman break galaxies, very, very high redshift galaxies, especially in images as deep as the Hubble Ultra Deep Field. This is the basic playground for people who hunt for the highest redshift galaxies in the universe. And these are just some of the properties. So again, this is now a more fleshed out type of spectrum for one of these Lyman break galaxies. This is a redshift 7 system. This is the UV. So in even the reddest of the optical filters of the Hubble Space Telescope, these will not be seen. It will be seen in the infrared in the Hubble Space Telescope, in Spitzer, just because we are seeing this intense UV emission shifted into the optical and infrared bands in our telescopes. And this is one of the highest redshift systems, redshift 11, confirmed through just very poor spectroscopy. Basically, the spectroscopy has to be broken down into a set of continuum bands. This is the highest redshift system. But again, we're speaking about star formation rates, which are a few times 10 to the 10 solar masses per year, well-formed stellar population of 10 to the 9 solar masses, and dark matter halos of around 10 to the 11 solar masses, not the type of systems that we are looking for proto-sphenoids. Now, if we take into account these two populations of UV star-forming galaxies at high redshift, at different redshift epochs, we will come to see this type of evolution through cosmic time. And this is the standard Maddow-Lilly diagram, in which it is shown that star formation peaked at redshift 2 through cosmic time. And this is the UV optical type of view, and we can actually try to reproduce the same type of view through infrared, and these are mid to far infrared observations. Notice that there is no information in this part of the diagram, and again the same picture emerges. Up to redshift 2, we have a rise in star formation, so star formation was much more virulent in the past around redshift 2, and then it went on decaying until our days. And what happens from redshift 2 to higher redshift is still a matter of investigation, because although we have a clear picture of what is happening in UV light up to the highest redshifts, the infrared part is missing for the most part. So this is one of the deepest views we have in the far infrared of the high redshift universe. This is exactly the same area as the Hubble Ultra Deep Field that I showed before, with tens of thousands of galaxies, but now in a very deep ALMA image at 1.3 millimeters, showing only 16 galaxies. But of course, our images do have much more information than just the galaxies we detect. We can do the stacking on the optical positions of the optical galaxies and trace how much star formation is hidden in the far infrared. And this is what is shown here. This is again a Maddow plot, in which we show the star formation rate seen at UV optical lights in the deep HST images, and we can see what is inferred in red from the far infrared image. And the black points will be the total star formation rate. Again, notice this diagram only reaches around redshift 4. There is not much more information in higher redshifts. So the picture that we have is the universe is very dusty, at least up to redshift 4, where most of the star formation is detected in the far infrared, not directly in the UV. And from redshift 4 onwards, this point shows us that if you correct by dust the UV light, then you will actually come to see all the star formation that comes at redshift 4. The expectation is at higher redshifts, if this diagram holds, still you will have most of the information carried by UV light. But notice the big error bars, and notice that this is a very small area of the sky, and therefore there is still much to explore at the high redshift in the far infrared. This is another view in which now, if you correct the UV light of star formation rate history by what you can see in absorption at UV optical wavelengths, you come to correct roughly up to redshift 2, the star formation rate history. But if you take this UV light and try to predict what the infrared sky, the far infrared sky will be like, this is what you will come to predict. Just extrapolating from the optical to near infrared view, you will predict that at Herschel or 1 millimeter bands, you will see this type of sky, and this is what is seen. Clearly, very bright objects in the far infrared cannot be traced by the extrapolation of the optical near infrared light. Our nowadays knowledge of how the dust properties and their re-emission into the far infrared works is very incomplete, and therefore we do need the direct images in order to reconstruct what the star formation history of the universe is in a complete view. Why is this important? Because we know, and this is just a diagram that shows how much energy is emitted in the full sky by astronomical objects against wavelength. This is if you go into dark patches of the sky and you integrate what is the background, you will see that the optical background comes to be this way. The optical background we know nowadays is just made out of all these optical galaxies that we see in this picture of the Hubble Ultra Deep Field, but extrapolated to fainter objects and to higher redshifts. This is what makes the optical background. And we do see the infrared background. And what makes the infrared background is something that nowadays we are starting to see through these deep images at far infrared wavelengths. But the message is the star formation rate and the infrared output of the objects along the line of sight at different epochs in the universe is as high, is as important as the optical output. So getting to know the universe and the star formation that happens in it in these wavelengths, since we cannot extrapolate it just directly from the UV optical view, is extremely important to understand the full history of development of our universe. So this is what has been done with far infrared and millimeter telescopes. And this is one of the iconic images of the deep universe taken by the 15-meter James Clerk Maxwell telescope. It is the view of the Hubble Deep Field, different from the Hubble Ultra Deep Field. It was one of the first cosmological fields to be studied. And through this image, the establishment of a new high redshift population to be studied and look at into whether this can be the answer to the proto-elliptical quest. So this is a very promising candidate. In the 90s and in the early 2000s, this new population, the submillimeter galaxy population, was proposed. It was found through deep far infrared millimeter images. And the surprise is the star formation rates that one can derive for this system do match the expectation for the proto-ellipticals. These are systems in their far infrared. This is the standard spectral energy distribution of one of these systems. You can see here wavelength. They are detected in the observer frame around 1 millimeter, really in this image at 850 microns. But you can see that most of the energy is emitted in this mountain here, which basically is the re-emission of dust, is the emission of dust of all the reabsorbed light that has been absorbed from the young stellar populations. So these galaxies are very easy to find in millimeter wavelengths. They have huge star formation rates. The calibration comes from all the re-emission of the dust in this part of the spectrum. And what you can see with these stars is that even if they are detected at, let's say, 1 millimeter, because that's the wavelength in which I operate the experiments like Aztec and Toltec in the large millimeter telescope, when this spectral energy distribution gets shifted towards the right because of the redshift of the expansion of the universe, your observed window goes moving up in this ladder. It goes sampling at redshift very close to zero. The nearby galaxies, you will be sampling this part of the spectrum, but as soon as you go to higher redshifts, like redshift 0.4, you will be over here. At redshift 1, you will be over here. At redshift 7, you will be over here. And at redshift 10, you will be over here. And this is the behavior of the light you're seeing. The light doesn't decrease and plummets through with redshift. It decreases certainly up to redshift 1, but then from redshift 1 to redshift 10, the dimming of cosmology, the fact that you are putting this object farther and farther away, gets compensated by you sampling the intrinsic emission of the galaxy closer to the far infrared peak. And so this is why the exploring the universe at millimeter wavelengths, at far infrared wavelengths, gives us a huge volume to look for these systems and to study how these proto-spheroid candidates do work. So what have we learned about these systems? This is just a bunch of properties that I will not go very in-depth into, but submillimeter galaxies are ultra bright, dusty galaxies. If you integrate the peak of emission, they come to have far infrared luminosities in excess of 10 to the 12 solar luminosities. Through that luminosity and the calibration with synthesis models, population synthesis models, one can calibrate the far infrared luminosity into star formation rates, and they come to be between 300 and 3,000 solar masses per year. They are extraordinary star-forming systems. The redshifts, with much work, because they are very optically faint, and taking an optical spectrum has always been and is being a problem, but now we are making progress with the millimeter spectrographs. The redshift population peaks at between redshift 2 and 3, and the highest redshift system go up to redshift 7. We know they are massive galaxies. In order to just go from a millimeter image, which is just basically a big blob of a very, very large beam width of around 30 arcseconds in the case of our observations of Aztec in the ASTI telescope. This is one of our images. You just have to go through interferometry in these very, very coarse type of maps, but that can cover large areas of the sky in order to find these systems. And then you can relate it to the deep HST images to find what type of morphology they have and to measure what masses they have. And the masses are measured through the optical photometry at different bands and matching it to again, population synthesis models. And the masses come to be around 10 to the 11 solar masses, so they are very well-formed galaxies, clear not with the mass of a nearby elliptical galaxy, but the understanding is that this is a system which is forming through time. And they are very optically faint. And up to now, what we have been seeing is that most of the submillimeter galaxies related them through the optical morphology and the optical images come to be kind of very clumpy disks. They do not have spheroidal morphology. They do have a type of disky morphology. Okay, so a lot of the work that we have been doing is with this camera that we have now retired from the telescope. These days, it is in the large millimeter telescope. This is the main facility I use for my research. It's a 50-meter dish located in a nearby centric position in Mexico. It's about 2 hours away from where I live in Puebla. But before, the camera was operated in the 10-meter ASTI telescope in the Atacama Desert, and before that, in the James Clerk Maxwell telescope, before the Scuba 2 camera arrived there. So we have 3 campaigns, one in 2005-2006 in the JCMT, and 2 campaigns in 2007-2008. You can see here the large teams I'm referring to. Many of the students that come to talk to me to just look for projects, they tell me, why do you publish with so many people? And the reason why I publish with so many people is that you need many people in order to operate these big campaigns. We're speaking about half a year in a telescope in order to take the images that I'm going to show you, which are just examples of the data that I work with. These are just some pictures of the teams just operating the Aztec camera, first in Hawaii, here in Chile. And this is the type of maps that we find. They are just blobs, they are just circles that show that we have detected a high redshift galaxy. But a lot of work needs to be done in order to discover the properties that I was showing you. So collectively, through the years that we have been operating Aztec in the 10-meter and 15-meter telescopes, we have collected about 3 square degrees of surveys. This is the work, as I said, of roughly a year of observations at these telescopes. And around 1,500 sources detected at signal-to-noise 3.5. Please take in mind this number, 1,500 sources, about a year of work, not only on these high-redshift galaxies, certainly in other systems as well. So as of millimeter galaxies, this is a diagram that we like to show. This shows how many of them there are in the sky per flux density band. So if you go to the very, very, very luminous systems, you find very few of them, about one of these 10 millijansky sources per square degree. But if you go to fainter sources, which are closer to 1 millijansky at 1.1 millimeter, then you find around 1,000. And we have a pretty good expectation, pretty good measurement of how many of these systems we can expect to find in any patch of the sky. Now, I would like to show how this relates to the infrared luminosity. With ASTI, we had this type of selection curve. This shows redshift against the luminosity of the systems we can find. And ASTI, because it's a very small 10-meter class telescope, it means that our selection comes above this line. So basically, this is the 1 sigma type of selection. So we will be typically looking at ULERC type of luminosities, ultraluminous infrared galaxy type of luminosities, above 10 to the 12 solar luminosities. When you go with telescopes at the 50-meter JCMT, even with the best cameras, Scuba 2, then you are basically bound to this other selection. This works at 850 microns, so the selection is not very different from that of ASTI. But when you go with systems like the LMT, the full 50-meter telescope that we have in Mexico, with a camera like Toltec, the camera that we will put in operation, hopefully next year, then you are able to detect systems which are above the luminous infrared galaxy, around 10 to the 10 solar masses per year, which is going to basically be a revolution. We're working now with Aztec, a much smaller camera, only illuminating the 32-meter telescope. Aztec has already been decommissioned, but I'm going to show you some of the latest results that we have derived with this. And this is a survey of 93 H-Atlas ultra-red sources. These are Herschel detected sources. Herschel has a very coarse beam size of around 37 arcseconds at 500 microns. And therefore, relating them to the optical properties is very difficult. But going through the LMT observations with the 32-meter illuminated dish, and this is how we were operating up to last year, we are passing from 37 arcseconds to 9.5 effective beam size arcsecond. Really, at these wavelengths at 1.1 millimeters, our telescopes, the 32-meter illuminated surface, had around an 8 arcsecond beam size. But in order to effectively reduce the data, we have to filter it with a Wiener filter, and this degrades a little bit the beam size. The red sources are defined as sources which are 250, have smaller flux densities than 350, than 500. Extreme red sources have this type of colors, and we are focusing on very luminous sources. And this is because Herschel has this very poor resolution, and we want to make sure that these sources are really robust. They are not just confused with peaks in the noise. But we are not going to the higher fluxes, because we know the highest fluxes are 100% confidence optically amplified. This color selection makes sense when you analyze a color diagram and you take one of the typical spectral energy distribution, this type of emission of the dust with a peak very well formed in the far infrared, and you shift it to higher and higher redshifts, and you analyze how they observe 350 over 500, 250 over 500 colors behave. What you see is a sequence of redshift. And so our selection technique is such that we are trying to select galaxies, which are color-coded in this diagram, above redshift 4, the highest that Herschel will probably be able to detect from there onwards up to redshift 6. So our integration for these 93 H-ATLAS sources are very quick integrations of 5 to 20 minutes. And we, of course, have a larger field around them. And what you can see here are some postage stamps of the H-ATLAS sources, these submillimeter galaxies discovered by Herschel. And some of them you can see a single source seen by the LMT. This is 10 arc-second beam size, these small circles, and the large circle is the 37 arc-second beam size of Herschel. And some of them are multiples. And what we find is that statistically 50% are multiples with beam at a beam size smaller or a size smaller than the beam size of Herschel of 37 arc-seconds. And we also detect that that we can find 23 extra sources around these Herschel sources in the surrounding field. Now, because we have a very, very clear view of how many galaxies we will expect with the LMT at 1.1 millimeters, because we had these very big surveys done with ASTI, which basically shows us the statistics of one source of 10 millijanskis per square degree to 1,000 sources of 1 millijansky at around in that same square degree, we can confidently tell that these 23 extra sources are strange in these small fields, because we were expecting from a blank field only 4 extra sources in our mapped surrounding regions, but we are finding 23. And the probability of having 23 sources out of a mean population of 4 sources in our total area is 8 × 10⁻12. So certainly what we are detecting are overdensities around these submillimeter galaxies. So the overdensity can be characterized is roughly of a factor of 4.5. And this basically speaks of submillimeter galaxies inhabiting dense environments. So these are just some other properties we are finding. We're finding some close in, hopefully interacting galaxies, although we don't have the redshifts for all of the pieces, and so this is just inference over the images. But relating it to the Herschel sources and running a photometric redshift code, we can tell that the peak of the distribution of all the sources, this is the sources associated to the Herschel sources, is 81% are above redshift 3 through photometric redshifts, 33% are above redshift 4, and 6 of these are spectroscopically confirmed because we have been able to measure them with our spectrographs also in the large millimeter telescope. So please focus. Our selection technique was such that through the colors, we were selecting galaxies that our templates of SMGs told us that they were above redshift 4, but just 33% are above redshift 4. Really, the confusion in the Herschel fluxes is such that the selection is much more effective around redshift 3. Okay, I said that they were overdensities. I just want to recall that this is no surprise. We know of a few very prominent sources like Aztec 3 that inhabits redshift 3. Aztec 3 is at redshift 5.3 in the cosmos field. This was one of our sources, but it was further studied by Riegers and Kapak, and they detected a bunch of objects. They detected first the redshift of the source, which was basically a problem since our first detection in 2007 of this source, and we had the redshift in 2010. And they also detected 11 other objects around them, in principle Lyman break galaxies, Lyman alpha emitters, but through the density of these surrounding objects, they could tell that Aztec 3 was in an overdensity of a factor 11 over the population. So our Herschel resources, our Herschel follow-up results do show up that this is actually a much more common situation than previously expected. I know that Karin is doing a lot of work on this. I'm sorry that Karine is not connected on full voice, but I know that her and her team are doing a lot of work on finding these superdensities as well. So the chances are very good that you will detect them. I'm going to now go into the description of some other properties, and instead of using the LMT surveys, I'm going to use the Scuba 2 Cosmology Legacy Survey. This is a very big survey done with the Scuba 2 camera, very fast camera, much more rapid than Aztec was. And we have been studying in particular a small field in the extended growth strip and analyzing the galaxies that we're finding. And I would like to show you what the latest results are on the dusty galaxy population, just the standard dusty galaxy population. These are not particularly bright SMGs. They are much more of a few hundred solar masses per year type of galaxies. So the survey was conducted or was analyzed in depth by Jorge Zavala, one of my former PhD students. These are just some of the galaxies. This is the position of the JCNT in blue, and in red you can find the galaxy, the optical galaxy that this is related to. And because Jorge did a very good analysis of what are the counterparts in the optical and near infrared in the HST images, we have been able to actually now go and compare them to the rest of the star-forming galaxy population. This is work done by Luisa Cardona, who is here receiving her master's degree. Now she's a PhD student. And what you can find here are just some comparisons of where the submillimeter galaxies that we detect in the Scuba 2 Cosmology Legacy Survey. They are marked with these red symbols. You will find diamonds, which are the star formation rate derived from the far infrared, and how it relates to the optical properties, which are just these triangles, red triangles, but inverted downwards. You can see that there is a huge difference. At any redshift that you look at, you're finding a huge difference. So one of the first results that we have, this is something that was known, is that most of the star formation comes in the infrared, and actually if you try to correct in the UV near infrared, even 24 micron detected fluxes, you find huge differences. 80% of the SMGs have star formation rates which are in excess of what you will derive from the UV infrared light, and the differences can be as high as a factor of 1,000, which is huge factor. And you can see in this plot that one cannot see any trend with redshift, and these differences go all over the different redshifts, and you cannot see also any difference or any trend with stellar mass, with the stellar mass of the counterpart of the optical galaxy. This comes to show just that in general, to the in comparison with the star-forming galaxy population, if you look at the specific star formation rate, which is the total star formation rate derived by the total mass of the galaxies. So star-forming galaxies do occupy the upper part of the main sequence of star-forming galaxies. They are, in general, much more virulent than your typical optically selected star-forming galaxy. And 71% of SMGs are above 1 sigma of the main sequence. Only 16% are above 3 sigma. And this is a measurement done consistently. I mean, we have taken all the galaxies in the HST images, in the EGS field, in the standard growth strip field, and analyzed them exactly in the same way. SMGs are larger. Their effective, this is the stellar mass. They are much more massive than standard star-forming galaxies. You can see the SMGs in orange here, and you can see they are a factor of 12 larger stellar masses than the standard optically selected star-forming galaxies. Their sizes are also larger. At any given redshift, except for the highest redshift, redshift 3, we are finding that SMGs are about 2 times larger than star-forming galaxies. This is their optical size. I would like to recall your attention, and I mean, if you have read this paper by Simpson et al., this is the comparison of submillimeter galaxies in the UDS, and compare their sizes to the submillimeter sizes derived from ALMA. The ALMA sizes, the infrared emitting region, is much smaller than the size of the galaxy in the optical, and this is clearly seen in this galaxy. So when we are saying this comparison is done through the HST images, the H-band HST images, and we see that these are about a factor of 2 larger. Now, in the literature, we ourselves in the Zavala results also said that we were seeing a sequence of concentration of the galaxies, such that when you go from the highest redshifts to the lowest redshifts, the galaxies seem to be more concentrated. And this actually went along the idea that the galaxies are forming their bulge. What we're seeing now in this new study, this is a paper about to be submitted, this is not yet submitted, is that indeed the CERSIC index, the concentration of the galaxies, goes on increasing up to higher redshifts, but, goes on increasing up to lower redshifts, but the general population, which is again in gray, actually suffers the same evolution. So we might be seeing the build-up of the spheroids, but it is the same build-up of the spheroids that standard star-forming galaxies suffer. Okay, I will skip this. Clearly, all this is done up to redshift 4. We do have, and this is one example, so I will not jump it, but this is an SMG found at redshift 6, and there are some SMGs found at redshifts slightly higher than 6, but we do not have a good demographics of what is happening here. And this is why we are building this new camera, Toltec. I am the project scientist for this camera, and this is our telescope, and this is the camera. The camera should have been at the telescope, but the pandemic is hitting on us. The camera is ready. It is in the UMass lab. This is Grant Wilson, the PI of the camera. And this is the optical bench where the 3 detectors at 1.1, 1.4, and 2.1 millimeters will acquire images of the sky at a much faster speed than our old Aztec camera could. So Aztec is decommissioned, is out of the telescope. The telescope is already prepared to take Toltec, and Toltec is waiting for a better pandemic condition to come to Mexico and start taking the surveys that we have promised. So the submillimeter galaxy studies that I have been showing you have been taken with these surveys here. This is the Scuba 2 CLS, the deep survey. And this is a type of service. This is optical depth against map area. This is the ultra deep survey that we will be able to take with Toltec. And we will take also a large scale type of survey with Toltec that basically brings us orders of magnitude from what the 15-meter telescope, JCMT, with the Scuba 2, which is one of the most advanced cameras, are right now. We will take in the first for 2 years of operation, read this 2021, because 2020, obviously, we are not taking any images. The camera is not yet here. We will take these 4 surveys, and there are another 6 surveys that are yet to be defined. The 2 that basically are related to the science that I have been talking about today are the Galaxy Ultra Deep Survey, which goes to the confusion limit of the telescope. It goes about 10 times deeper than what we have been able to go up to now. And the large scale survey, which goes 60 degrees to the depths that we have been exploring up to now. The areas are defined. If you are interested, please get in contact to me. And there is a big promise of discovering what is in this parameter space of dusty galaxies at high redshift that we still do not know. These are my main conclusions. There is still much that we need to derive from deeper surveys that the ones Toltec will take. But up to now, with the shallower surveys that we have been taking, we know some of the properties of the brightest of the submillimeter galaxies. Some of the results, new results that I have presenting in a couple of papers, that one of them submitted, the other about to be submitted today, is that 50% of the brightest Herschel sources are multiples. They are actually a signpost of overdensities. There are 23 extra sources, as I said, around the 92 sources, Herschel sources, and there is an overdensity of around a factor of 5 around them. Most SMGs are on the main sequence of star formation, but around 79% of them are of 1 sigma of the specific star formation rate track of star-forming galaxies, and this shows that they are extreme star-forming galaxies. They are about 12 times more massive than optically selected star-forming galaxies, about 2 times larger than optically selected star-forming galaxies. And although there is evidence for a morphological transformation through cosmic time, with Sersic indices larger at lower redshifts, for most of the time it is consistent with that experience by other star-forming galaxies. And redshift below 1 is the exception, but that's where there are fewer of the submillimeter galaxies because the population peaks around redshift 2 to 3. So we might be seeing the buildup of the spheroids at a similar rate as other star-forming galaxies in the field. And that's all I wanted to tell you about today. Thank you for your attention.
Thank you, Itziar.
I'm going to stop the screen unless somebody speaks about and makes a question about one of the view graphs, in which case I will retake the screen.
Okay. Thank you very much. This was very interesting talk with lots of exciting results. So congratulations for all these projects that you are participating in or coordinating. So very, very amazing work. So we have here some questions. So let's start with this question from Yana. She's a PhD student here in Valongo. So she wants to know about the AGNs in SMGs. Could they be buried into this huge amount of dust?
Thank you, Yana. And hello. I met Yana in the conference in Brazil, in Porto Alegre, near Porto Alegre, in Bento Gonçalves. So it's a pleasure to receive a question from her. I know that she was in the audience. Yeah, I haven't gone into the aspects of how many AGNs are buried in these galaxies. We do know from the optical spectroscopy taken by Chapman, and these are results from 2003, 2005, that a good fraction of them have AGN characteristics. So there is a very good chance that some of them do have AGN buried in them. Most of them might have AGN buried in them. And actually, there are a few theoretical works that relate submillimeter galaxies to the quasar population. And they pose the track of submillimeter galaxies being an evolutionary epoch that comes before quasars shine and have the nuclear part, the accretion into their central black hole be exposed. Whether this is true or not is still being analyzed. I mean, there are some works that basically support that idea, and some others that put in doubt that idea might be true. The AGN characteristics that have been found in submillimeter galaxies are weak AGN characteristics. I mean, they are Cipher-like type of AGN characteristics, not quasar-like luminosities in their emission lines, etc. But it could well be that they are just very buried and that you are not seeing it. X-rays also give you a different view, but complementary, but still not definitive about the percentage of these systems that might be AGN. But there are some studies around.
Okay, great, thanks. And also Yana comments that it's always nice to see you speaking. So she was excited about your talk. And she was excited about the work from Luca Cardona too. So we can pass the message along.
I will.
Okay.
Maybe she's listening to this. I have no idea. We used
Okay.
to have our group meeting at this time, but today we cancel it.
Okay. So the next question is from Thiago Gonçalves. So he says that measuring dust temperatures remain a challenge. ALMA reached high frequencies, but requires excellent weather and has a narrow field of view. So are there any future projects to map large areas at the 100 to 500 micrometers?
I am not involved in any of them, and Thiago is absolutely right. I mean, I'm deriving far infrared luminosities, but if all I have is the 1 millimeter point, I am not sampling the far infrared peak, and that is very important in order to derive the total luminosity, and that depends on the effective temperature the whole dust is radiating. So what we are doing up to now is using the 450 microns to 850 micron complementary data that we have in the fields for the Scuba 2 Cosmology Legacy Survey. That's a given because those two frequencies are sampled. And then, well, we are constraining a little bit better where the position of the peak is. Now, the Toltec extragalactic surveys that we will be doing, especially the deep survey that we will be doing, we certainly are going to go to areas of the sky that have been well studied by other telescopes. They are candle fields, basically. And so the JCMT is, with Scuba 2, is putting much more time into those fields. Scuba 2 cannot reach the same time of depths as we will with the LMT, so there will be a fraction of galaxies that certainly will not have the complementary or shorter wavelength type of maps. Can it be done with ALMA? Well, ALMA is able to do this type of depths, but it requires a huge amount of time. So it will require the full community getting together into a type of legacy survey to try to explore some of the sky patches, probably not all of the Toltec ultra deep field, in order to get the corresponding frequencies. But I guess we will need to wait until we have the LMT data, the Scuba 2 Cosmology Legacy, the Scuba 2 data that are taking now with the Eastern Asian facility. JCMT just came under Asian hands, Asian management in the last years, and they are continuing this type of deep service as well. And so we certainly communicate, and we certainly will pull our data together, and we basically can give a different something into a common project.
Okay, thanks. So we now have a sequence of questions from Karen. So let's start with this one. So she wants to know about the 23 sources that blended into the Herschel sources. So are they blended or too faint?
No, I'm sorry. I didn't express myself correctly. So 50% of the 93 sources are doubles. So they are multiples. But these 23 sources are outside of the Herschel beam. They are not blended with the Herschel beam. There are other sources that Herschel did not detect, but they are submillimeter galaxies, just that we can detect because of the better confusion limit that we have. I mean, we are not in the confusion limit, but of the better resolution we have with large millimeter telescope. And there are systems which are around the Herschel sources. They are submillimeter galaxies in their own right, but they are outside of the Herschel beam. Of course, we don't know whether they are at the same redshift. We only have positions. So this is something that we would like to investigate further.
Okay, and I will take the chance to, so I'm not an expert in extragalactic astrophysics, not my area of research. So was it something expected to get these 50% multiples or not?
Yes, I was short of time, and I wanted to give larger introduction into high redshift galaxies than into details of the submillimeter galaxies. But of course, we know a lot about these systems through ALMA observations as well. So ALMA has been studying both Herschel sources, but ALMA has a different beam size. is complementary to what we know right now with this survey. So the expectation was that many of them were going to break, because that's what ALMA has been showing, that single dish submillimeter galaxies, because we have a coarse beam. I mean, in the best case scenario, with Toltec, we will have a 5 arc-second type of beam. Right now, we have around 8 arc-second, and if you're going into the JCMT at 850 microns, you are 15 arc-second beam. So many of these sources do break into different systems, and this has been shown by ALMA. But the parameter space that the LMT gives, the separation of this breaking of sources is different, and many of these will have been missed by ALMA. So both things are complementary. Many of the submillimeter galaxies break into system. Others are single sources. And again, this is speaking about rich environments, not just one very big submillimeter galaxies going up, but many different galaxies going up at the same time in the same area of the sky, or maybe pieces of the same galaxy that will merge together just in the same area of the sky.
Okay, thank you. So next, I think it's more like a comment from Karin. So she says, Garcia Vergara, 2020, suggests that the connection between SMGs and massive halos is overestimated. They suggest that only the most extreme SMGs may be tracing galaxy overdensities. And then she proceeds saying that with Toltec sensitivity, we'll be able to detect many more of these fainter SMGs. So you might be able to uncover many more of those overdensities. Do you want to comment on this?
No, Karin is absolutely right. I am not claiming that all SMGs are in overdensities. The Herschel study were bright SMGs. I mean, they will have been the brightest SMGs, blank field SMGs. And some of them might even be amplified SMGs. And what we are showing that on average, they are in overdensity, but they will come in the same part of the brightness as this work that she is citing. And definitely, Toltec is going to be a huge revolution. I know that Karin is interested in the survey. I forgot to say, because I was rushing, but the Toltec data will be public. I mean, these are legacy surveys which are open to the full international community to exploit. So some of us are, of course, in the same team. We will have the data previously as the data is coming, but there will be 2 data releases, and the data will be just open to the whole community at the same time. So we hope that our Brazilian colleagues, friends, and collaborators will be interested in exploiting this data, hopefully with us, but they will be free to do by themselves otherwise.
Okay, that's great. Lots of interesting opportunities for future collaboration. So that's great news for the Brazilian community. And by the way, Thiago is excited. He wants Herschel 2.0. So he's suggesting that we move forward with this. And Karin says that she's definitely interested in collaborating. So you guys have lots of talk, and lots of people. Mariana says she wants to collaborate too. So people are really excited with the results and the data that are coming out of these surveys. And okay, so moving on. This is a comment from a question from Karin that connects with the one that I was going to ask. So she wants to know. I would ask you to comment a little bit more on the International School for Young Astronomers, because we have lots of students and young astronomers in the audience. And Karin also wants to know how the pandemics will affect when it will be revived post the COVID pandemic. So how is what are the main goals, the current status, and what do you envision for the future?
Okay, so this is a completely different topic, definitely. You mentioned it in the introduction. I am the director of the International School for Young Astronomers. These are schools basically organized by the International Astronomical Union for more than 50 years. They have been organized, and it targets students which are isolated, either in countries where astronomy is not fully developed, or in locations which are basically isolated from a big community where the graduate students can basically flourish. So this year we had a program, 2 schools, one in Mexico, where the Latin American community will have applied, and they did apply, and we had our students selected. It was to happen in June 2020 in Chiapas, Mexico. And the other one was a program to happen in Cape Town, South Africa in November 2020. Both schools have been postponed. They will not happen. Our schools are 3-week intensive graduate schools where about 30 to 50 students go and live with about 10 to 15 lecturers, and we are very, very intense experiences. You should talk to your fellow students from Brazil. Some of them came to the school in Colombia 2018, and they will tell you, we work hard. We work extremely hard. Actually, Karin was lecturing in that school, and Thiago was also there as a support person for the whole school. So what happens? Well, the pandemic has hit, and we early on decided that it was not safe to have them face-to-face. The style of the schools do not make it easy to make them online. Most of the work that we do is hands-on. A lot of the work we do is hands-on, and a lot of the work we do is to create the community, to basically bring together the students and give them a sense of belonging and a sense of tools that they will have both to develop in a professional way, in a personal way, and the links to the international community. So that is very difficult to do over online schools, but 2021 does not look very promising. We, in principle, have postponed them for June 2021 and November 2021, but we do not see it happening in a safe way, because we're bringing students from many different countries, and that requires to have a safe environment from the sanitary point of view, and also from the coverage for these people to be able to travel and visit a different country. So what are our plans? Well, our plans are, we are talking to the local organizing committees of these schools, and we are seeing whether we will be able to organize part of them, at least in an online fashion, until the conditions are safe. We still do not have the commitment, and we don't know whether there will be the resources to do them for the 2021 Mexico school. We do know that the 2021 South African school will happen, but for Brazilian students or for the rest of the Latin American students that might be connected right now, the Mexico school will be the one of interest. If that doesn't happen, well, we are hoping that for 2022 the condition will be better and we will be able to go back to the face-to-face type of a school. But at least the South African school will give us a taste of how we can operate, what part of the program we can carry online, and then just plan from there. But this is as much as I can tell you. We are worried. We are concerned on how to push forward with the program. But we see serious difficulties in having such an intense environment and a school carried out through the internet. So next year will be an experiment. This year we decided we were going to give ourselves a chance of seeing whether next year was going to be better. But I think we all are now convinced that by June 2020 we will not be able to do it in a face-to-face fashion.
Okay, thanks. Anyway, it's very, very important that you guys are thinking on ways on moving forward on this very important initiative. And Karin comments that we had 2 students from Valongo that participated in the 2018 edition. So if anyone in the audience wants to contact them to learn about the experience, so they are very active in the social media, so it's easy to find them. And on this note, we come to the end of the questions and comments. Itziar, so I would like to first congratulate you from your work with the International School. It's a very important work, and also on your research and all these projects and very interesting results that you are obtaining with your group and your collaborators. So it was a great pleasure to learn more about your all initiatives, outreach and research here. And thank you very much for accepting our invitation. So do you wanna leave any final words to the audience?
Yeah, definitely. I didn't put up my email, but I have a very unusual name. So if you look for my email for my name, Itziar, and Itziar Mexico Astronomy, you will find my webpage, you will find my address, and you are more than welcome to get in contact with me to ask about any of these issues, the SMG research we are doing, the Toltec programs that we have in mind. I have just been talking about the galactic astronomy projects that we have planned, but we have galactic astronomy projects planned as well, which will be legacy surveys of our own galaxy, surveys for core protostar type of analysis, magnetic field analysis in our own galaxy. So please feel free to contact me and just speak about what your wishes are in research, whether those programs will actually be of interest to you, what other programs you might want to do with Toltec. We are very open to collaborate around the world, specifically in this legacy service, and there are 6 legacy surveys that they are still to be defined, and that depends on the community, on our community, on the LMT community, but definitely on our links to the international community. And also, if you want to know about ISIA, please contact me, of course.
Okay, thank you very much. Lots of interesting opportunities, different fields. So people feel free to contact Itziar, and if you want, you can type your email there in the chat.
Where can I do that? In the chat? Oh,
in the
okay.
chat, and then it will be on YouTube, and I can put it on the screen here. So let's see. Oh no. Okay, I can put this. It's on. I
think it went private. It says private chat.
Yeah, but I can put it here. So okay. It is now on YouTube, and I can put it on the screen here. So if anyone has any questions.
And you can also find me. I usually tweet. I am in Twitter. I'm a Twitter. Okay. So you will find me in social media as well. Okay. I do reply.
So I will put this here. So this is how to find her on social media too, and she replies. So that's very important. So Itziar, thank you very much again. It was a great pleasure having you with us. Hopefully one day when things are better, you can come visit us. So
come on, I will stop her going to Rio. Are you kidding?
So you're more than invited to come here. And it was a pleasure, and thank you very much for all of you that are in the audience. So don't forget that we are here every Tuesday at 2 p.m. Next week we have another talk. It's Sarah Seeger, so she'll be talking about exoplanets. And please feel free to check our entire schedule on our website, and don't forget to subscribe to our YouTube channel and our social media so you can get updates on the lectures that we have every week. So thank you very much again for being with us, and hope to see you next Tuesday. Bye-bye.
Obrigada.